Okay, move on into the last part for light. Before we start this, let's go into some recap of some of the theory that we have learned before. Okay, you may pause the video to think about the answers to these two questions. A light ray bends away from normal when it travels from an optically denser medium to an optically less dense medium. Okay, the answer is true. Okay, because you must know that every time it enters a less dense medium, it bends away, and when it enters a denser medium, it will bend towards the normal. The second question, in order for total internal reflections to occur, a light ray must select all that applies. You need to know that there are two conditions for total internal reflections to occur. The first one is that light must be traveling from an optically denser to an optically less dense medium. So it must be like from glass to air or water to air. It must be from denser to less dense. Okay, so it can bend away from the normal. So B must be correct. Okay, and next, other than traveling from denser to less dense, the angle is very important. The angle of incidence must be greater than the critical angle. Okay, so the answer is B and C. Okay, we are moving on into the last part, which is about how does your converging lens work. In this chapter, we'll learn about how does a converging lens works. We will learn the terms that is used in converging lens, specifically focal length, which is very frequently asked, and then we draw ray diagrams to illustrate how image can be formed by using a thin converging lens. And lastly, we will study about the characteristics of the image formed by your converging lens. Okay, where are converging lenses often used? They are often used in microscope to magnify images, and they are also used in magnifying glass. Okay, so if you take a look at a piece of magnifying glass, you will realize that they are always thicker in the center, which looks like this. It's thicker in the center and thinner at the two ends. Okay, so the shape is like that, fat in the center. So all lens or all glass or plastic piece that are shaped like this, they have the ability to focus or concentrate light into a single point. So they are known as converging lens. Okay, so there are different types of converging lens as well as diverging lens, but we will not be studying about diverging lens. So converging lens, you have this one, biconvex, semi-convex, and etc. lens. Okay, so converging lens are all taken in the center, but diverging lens, on the other hand, will be thinner at the center. Okay, so next we move on into the terms that you need to know for your converging lens. Okay, so the first one, let me just use my laser pointer. The first one you should know is called your principal axis, okay, which is over here. The principal axis is just a line, a straight line that passes through the center of a lens. So your lens is this blue color thing over here, okay? The center of the lens is known as the optical center, C, big C, represented by big C. It's over here, this dot over here. Okay, so the principal axis is just a line, a straight line that passes through the optical center of the lens. Okay, next, we have the principal focal point, or we call it the focal point or principal focus. Okay, we represent it by the letter big F. Do not confuse it with focal length, because focal length, later on I will explain in that, is represented by small f. Okay, the focal point or the principal focus is represented by big F. Okay, so for big F, it is the point where all the light rays will converge to it. If the light ray passing through the lens are parallel to each other. So you can see there are two examples over here. They are all parallel rays passing through the lens. Just that this is parallel to the principal axis and this is not parallel to the principal axis, but they are all parallel rays. Okay, if it is parallel to the principal axis, then all the rays that passes through this lens will all be focused onto a point known as the focal point or the principal focus of the lens. Okay, and this principal focus will always be on the principal axis. And then we have a line that passes through the principal focus that is called the focal plane, which is over here. So you can see that yeah, this is the focal plane. But if I have a parallel beam of light that is not parallel to the principal axis, obviously it will not converge at the principal focus, but it will converge at a point below it, but it will also be along on the same plane as the focal point, which we call it the focal plane over here. Okay, so it looks like this. Okay, next page. So focal plane, I've already explained, it's just a line. It's just on the same surface as the focal point. Okay, and most important, you must know and must memorize, is known as the focal length of the lens. Okay, the focal length is a length, it's a distance. Okay, it's not a point. This is a focal point, but focal length is the distance between the center of the lens, the optical center of the lens, to the focal point. Different lens have different focal length. They focus light at different length depending on the thickness and the material of the lens. Okay, so how they bend the light rays will be slightly different from one another. Okay, so remember, so this focal length is represented by small f, so it's this distance over here between optical center and the focal point. Same for this diagram, it's between the optical center and the focal point. Okay, next. Okay, we move on into ray diagrams. How to draw ray diagrams. There are three basic rays that you always follows when drawing ray diagrams, and they must be followed in order. You always draw the first ray, then followed by the second ray. The third ray is optional, but we will just learn in case they ask you to draw the third ray, because in most of the ray diagrams, you only need two rays to determine the intersection point. The point where the two rays meet will be the point where it intersects, and it will be the point where the image will be formed. So the third ray is quite optional. Okay, so the first ray is coming from the object. Okay, it will always pass through straight through the optical center of the lens to the image. The second ray will always be parallel to the principal axis. Okay, and then once it reaches the center of the lens, I will pass through the focal point F of the lens. Okay, and it will again meet at the image. The third ray is, it will pass through the focal point. It's opposite of the second ray. It will pass through the focal point and then becomes parallel to the principal axis. If you realize the ray 2 and ray 3 are exactly opposite, then it's straight, then pass through F. This one is pass through F, then straight. Okay, they're exact reverse of each other. Okay, so let's take a look at an example of how the 2 or 3 basic rays are being applied. But in this diagram, we use the 2 basic rays, which is actually sufficient already. Okay, so you have, how do we draw ray diagrams for lens? Okay, we draw a flat line which represents the principal axis. Okay, and then we draw lens. We use double arrow to represent lens like this. Okay, at the center of the line, the principal axis. Okay, then we mark out the focal point. Okay, the focal point is capital F. So let's say I tell you that the lens have a focal point of 2, or have a focal length of 2 cm. Okay, so the focal length is between the center of the lens to the focal point. So the focal length is 2 cm. So you measure 2 cm on the left side of the lens, 2 cm on the right side of the lens. Because light can pass from the left to the right, light can also pass from the right to the left through the lens, both directions. Light is possible to pass through. Okay, so I mark out 2 cm, F, big F, big F. And then usually I will also draw 2F, because later on you will realize that there are many different scenarios and some of them involve 2F. Okay, 2F will be another 2 cm, so it will be 4 cm away from the lens. So this is 2 cm, then another 2 cm, then you mark out 2F. You can draw on this side 2F as well. Okay, then after that, how do I represent an object? The object is usually represented again by arrow. Okay, but not necessarily is always an arrow. Sometimes they can draw, the question can come out in any form, but usually we use arrows to represent it so that it's straightforward and simple. Okay, so this object O is this green arrow here, and then I label it with O. Okay, so the first way I'm going to highlight for you, how do I get where is the image? So I have this object O, I place it in front of the lens. Okay, then now I'm going to, hang on, Okay, then I'm going to draw my rays to determine where is my image. Okay, so I'm going to draw my first ray. I'm going to highlight it. I will take the arrowhead. Okay, then I will pass through the optical center of the lens, which is this ray over here. Okay, my highlighted yellow one. So I draw all the way straight down. I don't know where's the image yet. Okay, but the image must lies on this ray. After I draw already, I need to put arrows. Okay, there must be arrows before the lens and after the lens. Okay, so that's my first ray. Then my second ray, let me highlight in green. No, let me highlight in another color. Let me highlight in blue. Okay, the second ray will always be parallel to the principal axis. Okay, over here. And then once I reach the lens, I will pass through the focal point of the lens. Okay, so I don't know where it will end up, but I'll pass through the F. Okay, focal point. And then I just draw it straight. Oh, and I will realize that, okay, the two rays will intersect. The ray must be on the yellow line. It must also be on the blue line. The image must be on the yellow line. The image of the arrowhead must also be on the blue line. So it is the point where the two rays intersect over here. So this is actually the arrowhead and the image of the arrowhead. So I just draw the arrowhead over here and it is to the axis. Okay, the axis, principal axis. So this will be my image. I label it as I. Just take note that in real life, you not only have two light rays shining onto this green object over here, you have millions and billions of light rays. But I don't want to draw millions and billions of light rays. So I only just draw two light rays to help me determine where will be my image of this arrowhead. Okay, so for the same for this, if you were to take a point that is not at the arrowhead, that means at the center of the body, okay, you draw the first ray, pass through the optical center of the lens. Okay, and then again, the second ray that is parallel to the principal axis, and then pass through F. Okay, then, oh, I meet at this point. So this point is actually the midpoint. So if I were to draw my image, okay, my image will be somewhere here. This will be my midpoint of my image. Okay, this will be the midpoint of my image over here because this part corresponding to the midpoint of the image. Okay, so next, after you learn to draw ray diagrams, we need to describe the image. So there are three main things when we want to describe the image. We call it the characteristics of the image. The first one is whether is the image real or virtual. You have learned about mirror image, or all the mirror image produced are virtual image. But for your lens, you can actually produce real image. And most of the time for lens, you get real image. So what happens is a real image. So for example, just now the example, the object is on the left side of the lens, the image is on the right side of the lens. Okay, once the object and the image are on opposite side of the lens, we say that a real image will be formed. And if I put a screen over here at this point, okay, I will be able to capture this image on my screen. It's called a real image. Okay, so there are characteristics. Most of them are real. A real image can be formed on screen. A virtual image cannot be formed on screen. I will show you examples of how lens can form virtual image later on. Okay, the next one, we say that we are concerned about the size of the image. Okay, the size can be either magnified, same size, or diminished. Magnified means it's bigger. How do I know it's bigger? I just measure the height of the image as compared to the height of the object. If the height of the image is larger, then of course it's a magnified image. Diminished will just be smaller. So if you take a look at the examples previously again, this is a magnified image. You measure this height of this image is greater than this object. So it's a magnified image. Okay, it's bigger than the original object. Okay, next. Okay, next one is about the orientation of the object, vertical orientation, whether the object is upright or inverted. If it's upright, means that the image is in the same vertical orientation. If it's inverted, means it's upside down. So if you take a look at the example previously again, okay, my arrowhead is pointing up, but my arrowhead is pointing down. So it's actually upside down. So this is an inverted image. Okay, the image is always compared with the object to see whether it is inverted or upright. Okay, so upside down is inverted. Opposite of inverted, it will be upright. Okay, so these are the three characteristics that we use to describe images. Then let's move on. In your textbook, you will see this entire table because what happens here is when you place your object at different position relative to the lens, you get different type of images. And that is how lens is being used in many different situations. By adjusting the position of either the lens or the object, you can get many different functions by using the lens. Okay, so but I only need you to memorize 3 important cases. Then the rest you can actually derive from it. Okay, so you take a look at the first column. It's actually the object distance. They represent it by U. Okay, so when the object is from a very, very, very far away object, okay, so we say that the object is super far away from the lens. U is infinity. Okay, you need to know that the light rays that strikes the lens will always be almost parallel to each other. Okay, so you should also know that if I am parallel to each other, my rays will always focus exactly at the focal point. But of course, this is not exactly at the focal point, it will be at the focal plane. But my image will be exactly at F over here. So the image distance will be at F. Image distance is represented by this V. Okay, and then you need to memorize the uses of this. This type of lens is used to see very, very far away objects like a telescope. Okay, next one, you can see over here, if my object is placed still quite far from the lens, is more than 2f, That means if the focal length is 2 cm, then the object is placed like 5 cm, is more than 2f. 2f is 4 cm, 2 times 2, 4 cm. Then if I place my object at 5 cm from this lens, which has a focal length of 2 cm, then it will be like this. It's not like placed at 100 million cm away. This is only placed at 5 cm, so it's still quite near to the lens, but it's more than 2f. Okay, then you were to draw your rays again. Okay, you will be able to get that the image will be quite small. The further away from the lens, the smaller the image will be. So we say that you can see that it's upside down, it's inverted, it's on the opposite side of the lens, so it's real, and it is diminished, it's smaller. So where do we often use this? This is when we want to have big object captured onto a screen as a small object. We use this in our camera lens, where we can take a photo of an entire person, and then the entire person can be focused onto the film, which is a smaller area or smaller picture, okay, on the film. You don't need a film that is as big as the entire person. Okay, so okay, then we focus into the first case that you need to memorize. The first case that you need to memorize is objects that comes rays from far away objects when the object distance is infinity. You need to memorize that it is always parallel, and it will always focus at the focal point or the focal plane. So why is it considered parallel? You can take a look. The sun is a very far away object. Okay, so if I were to place a converging lens on a table, I can actually capture light from the sun to form an image. Okay, but you know that the sun doesn't give out light that's parallel to each other. They give out light in radical directions like that. Okay, but by the time it travels to the lens, okay, they are almost parallel to each other already, like this enlarged version of the lens. Okay, almost parallel. So when it's almost parallel, when it passes through the lens, it will focus at the focal point or the focal plane. Okay, so you can take a look at these few examples. A tree from a faraway tree, maybe like at least 50 meters away from you, that's considered quite far away. Okay, so you have rays that comes from a tree, they will all be parallel to each other, but in this case, not parallel to the principal axis. So I will focus at F. Okay, the principal focus here. Okay, but it will not be exactly on the principal axis, it will be on the focal plane. So the focal, this can be used to determine the focal length of the lens. So the focal length of the lens is actually from the optical center of the lens, which is this 40 mark, to the screen, where I get a sharp image of the tree. Okay, so the focal length is actually 40 minus 10, 30 cm. Okay, same for this. If they are parallel, or the trees, if the light rays hits the lens parallel to each other and parallel to the principal axis, then I will focus at the focal point. So the distance between the optical center of the lens all the way to the screen is the focal length. And this is the focal point of the lens. Okay, next one that very important, you need to memorize. I need you to memorize. So the first one is when object distance is very, very far away. You need to know that the light rays that strikes the lens is parallel and it will focus at the focal point. Now, I need you to memorize when the object is placed exactly at a distance of 2f from the lens. U equals to 2f, like this. Okay, so again, if my focal length of this lens is 2 cm, then 2f will be 4 cm. So if I place my object at 4 cm from this lens, which have a focal length of 2 cm, my object is at a distance of 2f. You need to memorize for 2f. When the object is placed at 2f, the image form will also be exactly at 2f, and it will be the same size. Memorize. Okay, so it's still real because it's on opposite side. It's still inverted, upside down, but it will be the same size. So what are some of the uses? It's used to make photocopying machine to make copies of the same size. Okay, why do I only need to memorize this? Because the rest of the others can be derived from here. So I'll tell you how do I derive from here. Okay, so you should know this already. You should already memorize. If my object is at 2f over here, AB, I will get my image, which is also at 2f. It will be real, inverted, and same size. Okay, so if I were to shift my object, okay, to my right, shift to my right, shift to my left, the blue color. Now my object becomes the blue color arrow. My image will shift together with my object, if you can see. So it will shift together in the same direction. So the rays are going downwards like that. If my image is shift nearer towards the lens, then my image will be smaller. The further away the object, the smaller the image will be. Okay, so now my object will still be real, will still be inverted, but it will be diminished, and it will be between f and 2f. Okay, but what happens if I shift my object towards the right? So now my object becomes this green one. If I shift my object towards the right, my image will also shift in the same way. So my image will shift to the right as well. So again, based on the ray going downwards, my image will now not be the same size, but it will be bigger than 2f, at a distance further away from 2f, but it will be real, inverted, and magnified in this case. Okay, and so that will explain the rest of the other diagrams, which I don't explain in depth over here. Okay, the next one that you need to memorize is this. Okay, when the object is placed exactly at the focal point, you will not get any image, because if you were to draw your rays, you will see that the rays will come out to be parallel to each other. There will actually be no image, or we say that the image is at infinity. You can't really see the image. This is often used in spotlight. Okay, so we say that this is used in spotlight. Okay, but this is seldom tested. The more often tested one will be this. Okay, so the first case is when objects are very, very far away, image will be at f, okay, at the focal point. Then the second case that you need to memorize, when the object is at 2f, image will be at 2f and same size. Now, you need to memorize the third case, which is also the last case that you need to memorize, is when the object is less than f. Okay, so what happens is, again, I'm using the same lens, which has a focal length of 2 cm. But now I'm going to place my object very, very close to the lens, such that it's less than 2 cm. Let's say I place my object 1 cm away from the lens. So my lens is very close to my object. Okay, then something very special will happen. Okay, if you take a look at this, okay, you will realize that if I were to draw my ray, first ray pass through the optical center over here. We draw first ray that pass through the optical center. And then the second ray that pass through straight parallel to the principal axis and pass through F. You will realize that these two rays are not parallel, so they will meet. As long as they're not parallel, they will meet. But they will never meet on the opposite side of the lens to form a real image. To get a real image, I must form on the opposite side of the lens as the object. But I will never meet here. This side will be going further and further and further away. So how will I meet? Okay, you will realize that I need to trace back. I will still meet. These two rays will still meet, but it will meet backwards like this. Okay, so I'm going to extend out my two lines until they meet. Okay, so I will meet at this point. So this point will be my arrowhead. Okay, and this point is on the same side of the lens as the object. So now I no longer have a real image. I have what we call a virtual image. If I put a screen over here, it will not form anything. It will not capture anything on the screen. So it looks like, my image is there, but it's not there. Okay, this is exactly how a magnifying glass works. You put the object very near to the converging lens, then your words appears to be bigger, or your object appears to be bigger and is on the same side of the lens. It appears to be behind the object and it's bigger. Okay, so we say that the image is actually virtual, it's magnified, and it is upright. Can you see that it's not upside down? The object arrowhead is upwards. The image arrowhead will also be upwards. So it's upright, virtual, and magnified. Okay, so this one, third case that you must remember, whenever the object is placed super close to the lens, such as less than f, okay, the image becomes virtual and magnified. It's often used as a magnifying glass. Okay, this is another example that shows you about how do we form virtual image or as a magnifying glass. Again, you can see that now my object, instead of upwards, I draw it downwards, but it's the same principle. Okay, my object is less than f. So the first ray I get must pass through the optical center of the lens, the yellow ray. And then the second ray is the green ray, must be parallel to the principal axis, and then pass through F. Then I will never meet here, so I need to trace back. Okay, I will meet at the same side as the object. So I will meet over here. Okay, then, this will be my arrowhead. Okay, so again, this is magnified, it's virtual because it's on the same side, and it is upright, it's in the same orientation. It's not upside down of each other. The object is already pointing downwards. The image is also pointing downwards. So it is upright. Okay, so one of the uses is magnifying glass. Okay, so let's take a look at a few word example. You can read the question. Okay, let's go through. Okay, I will skip reading the question. You can read yourself. Okay, so you see this is a ray diagram of an object and this is the image. They ask you to explain whether the image is real or inverted. You should know that the image is real or virtual. The image is virtual because it's on the same side as the object and it cannot be formed on the screen. Next one, whether the image is real or inverted. Okay, it is upright or inverted, sorry. Whether the image is inverted, no, the image is not inverted. It is in the same orientation, so it is actually upright. And then is the image magnified? Okay, very obviously you can see that this length will be greater, the red color length will be greater than the green color length. So yes, the image is magnified. And then describe a scenario where this setup is useful is as a magnifying glass. Next one. Okay, in which of the regions, okay, 1, 2, or 3, would an object produce a magnified image? Oh, so this, let's come back to think about our case study, okay? We say that the thing that I asked you to memorize, I want to get magnified image. I never say I want to get real or virtual. So it can be real or virtual. So I ask you to memorize, if my object is at 2F, over here, okay, then my image will also be 2F. And it will be same size. Okay, but now I do not want same size. I want magnified. In order to get a magnified image, what happens is I need to shift it nearer to the lens. Okay, so if I shift it nearer, so 1 is confirmed up. Okay, if I shift it nearer, then my image will shift in the same direction and it will become bigger. So this is magnified. So I can shift it to region 2, and I can shift it all the way until region 3, where it's less than F. When it's less than F, then again, I produce a magnified image because it works as a magnifying glass. So the answer is 2 and 3. Okay, next one. Let me erase this first. Okay, you can read. An image is produced by the lens as shown. By drawing more rays, find out where is the object orientation and location. So you need both orientation and location. Okay, so you know that this is my image. All my light rays must pass through my image. So they have already drawn the second ray for you, but you need to draw the first ray. So the first ray, I don't know where is it, but I know must pass through optical center, and I know must pass through the image. Okay, so I draw, which is this blue color line. Okay, so this one will determine where is my arrowhead. So my arrowhead will be over here. Just draw a little bit. Okay, so my arrowhead will be over here. Confirm. Okay, now, then where is my image? It doesn't only go to the axis, because can you see that I exit over my axis? Okay, so I need to determine where is this end of this image. Okay, so on the other side, I also draw the first ray that pass through the optical center. Oh, it must be here. Okay, it must be a straight line. Okay, so the entire image will be exactly at here, if you can see. Okay, let me erase this. So this will be my image. Okay, so the orientation, it will be inverted. Okay, because the object is upright, and then the image is inverted. So the object is inverted from is upright lah. The object is upright, image is inverted, and then the location will be exactly at here. Okay. Okay, next one. We move on. We have finished about how converging lens work. We are going to use applications of converging lens. I'm not going very in-depth into this. You can read from the textbooks. Okay. Your spectacles, okay, are made of lens. Okay, some of them are converging lens and some of them are diverging lens. Okay, so for converging lens, it's often used to correct long-sightedness. Long-sightedness is for people who cannot see things that are near you. Okay, so what happens here is when you have a lens, okay, the lens will be able to focus the light ray onto the back of your eye, your eyeball, which is called the retina. Okay, you need to have the rays converge exactly at this point. If you don't converge at this point, then you converge at the back or at the front of the eyeball, then you will get a very blurred image. Okay, so in order to converge here, you can see that light from a close object, it will not be parallel, it will spread out. Okay, so I have a converging lens to help me push it nearer to each other to converge a little bit first before I enter my eyeball. Okay, and then also we use a lot of lens in camera. Okay, the better cameras have lens that you can zoom in, zoom out better. Okay, by zooming in and zooming out, you are varying the distance between the object, which is whatever thing that you want to take photo of, and the lens. Okay. Okay, that's it.